because you can't access any data because the data node is down. It just knows, it just has the data stored. Your hard drive, when you pull it out of the computer, it's dumb. It knows nothing unless you actually plug into the computer and the operating system can see its metadata. Your hard drive is down, correct? That's the same thing. If the name node is down, your entire cluster is useless. And that is the reason why you have something called a standby name node, okay? Not secondary name node, standby name node, okay? Secondary name node, there is a thing called secondary name node, which has a different purpose to it, unfortunately named. But standby name node, typically in a large cluster, they will have something called a standby name node, which when the name node goes down, it comes back and stuff. Otherwise, the alternative is that you just restart the machine after a while, that's it. Yeah. Okay. Yeah.
Can I also confirm that where does the data chunking actually take place? Does it take place at the client level, or it takes place at the yarn level?
The splitting.
Yes.
The splitting takes at the client level. At the client level, because before even you go to the name node, you just request for storage of a block. You don't request for storage of a
Then
block.
after that, you set the metadata to the name node.
That is correct. That is correct. Yeah. Yeah, it's the same command, right? So how do you see HDFS, DFS, LS, and then you can see the file ACS itself. The RWX, that's what you're talking about? Or how do you give access permissions to the other graph? It works the same way as any POSIX systems, just like Linux, not like Windows. Yeah?
So extending from that question, who does the name node decide access level permission?
No. So name node just gives, when you copy the file into the cluster, I'm sorry. It just gives because you are the owner, right? So owner, the default permissions would be granted to you. So owner is say I think 700 if I'm not wrong. You can try that because your local machine is not enabled for security because everyone is free to do whatever you want. But we'll look at it tomorrow how to actually restrict how to actually secure your file system. But I think the default when you copy, I think it's 755 or 700. You can actually look it up. When you put a file, I think you can see from ls-r you'll be able to see what access you've been given. And then you can do a chmod as well. So if you wanted to open up, so you can do a HDFS, DFS, chmod. Typically you do, so if you want to do a recursive, then you do a 777 on your file. You can give whatever you want. It's just a standard Unix command. There is nothing fancy about it. Yeah.
Do you have any backup for the name node?
Backup for the name node. Yeah. That is the purpose of the secondary name node. So the dictionary thing which I was talking about, right? It's in memory, right? But what if you restart and memory is gone, the memory is wiped out, and even if you restart, no point in doing that. So what it does is that there is a node called secondary name node. What it does is that the name node internally, when it puts into memory, after a while it copies those contents of the memory into the local machine, in its own local machine.
Secondary name node will be in some other location?
Some other machine. So the name node itself, what it does is that whatever it has in memory, what is the file and the machine information, whatever it has in memory, it dumps into the local machine. And the only purpose of the secondary name node, you can imagine that as a unappreciated guy, an important guy. So what it does is that it just copies these files into its own local machine. So there is a backup.
Is there a level of secondary node, like only one secondary will be there or 2 or 3?
No, generally there's one.
Like it both goes down, like both.
Yeah, both goes down, yeah, that's it. Yeah. Wow. Yeah. Yeah, really pessimistic about your cluster. Alright, okay. So that's okay.
And one more thing.
I'm sorry.
Like scheduler, you talk about scheduler, right?
Yeah.
Is there any technique for scheduling, right?
We will see that shortly. We will see that in detail. Okay? One by one. Okay? Alright, okay. There's one more thing which I forgot to mention, that the way that your data node gets chosen while copying, right? So this is your name node, and then data node, in a larger environment, right? So when you're copying from the client, what it does is that the name node first chooses these data nodes randomly. When I say random, it also takes into consideration the computation which is running on the machine as well as the storage it has on the machine. So out of all the candidates, it just picks up one random, okay, among the candidates. Okay. So assume that this is the machine which is chosen. The second machine, if you have multiple racks on your cluster, it always looks up for a rack which is not the original rack which was chosen. Okay? So you have one rack here. So assume that this is another rack that you have here. So yeah, and these two machines belong to one rack. Okay. So the first machine, say you chose this machine, okay, to copy the first replica. The second replica will always be, if you have multiple racks, it will always be a different rack. So the reason why it does is that because you wanted to have maximum replication. That's the only reason. Okay? You don't want, because if one rack fails, then it's a single point of failure. We don't want that to happen. So it actually makes sure that it copies to another one. But most of the time, this is not for practitioners or big data users for us. We don't care about it because it's predominantly for Hadoop admins. But you should be cognizant of the fact that there is something which is happening here. Your data is safe. That's all we need to know. Okay. All right. The next thing, to your point, let's come to Yarn. Okay. So Yarn, we know that your HDFS is a storage mechanism, right, where you store the data. Yarn is your CPU and the memory manager, right? That's a scheduler. Okay? So Yarn has a very similar architecture as well. There is a master. There's a bunch of nodes, workers attached to them. We don't call them slaves anymore. So the master is called as a resource manager because it manages the resource, right? It manages the CPU and memory resource, but it's called as a resource manager. And the machines and the workers are called node managers. Okay? And the node managers, or NM for short. NM for short. So when you at any point, just like name node, Yarn has this. Yarn has information about what is the computation which is running on that machine at any point. And not only computation, how much of memory is being used at any point, or how much of CPU cores is being consumed at any point based on the jobs which has been run in that machine. Okay, I said jobs. We'll come back to what a job means. Okay, so assume that you're submitting, the client is actually submitting a Spark job or a MapReduce job. So when your program is actually submitted to Yarn for running, it becomes a job. It's as simple as that. Okay? Because it is once up until then your program is just a piece of code. Now you're going to run it on. You're going to use computation to run it. So it's just like you're running a local program, right? Up until then it's a part of code. Then it's going to start consuming CPU and memory resources. Okay? So you're submitting your request to Resource Manager. And Resource Manager knows, say assume that you're going to, what do you call it? You're needing, say, 10 cores. Okay? 10 cores, I need 50 GB of memory. Okay? Something like that. So, and then you notice that this node manager, all the node managers are free. Okay? So now, remember I told you that each of the HDFS files is split into blocks. Okay? So each of if the file is greater than 120 MB, it will be split into several blocks. So 512 MB is the example that we saw. It has 4 blocks. And these blocks are also called as partitions because they are literal slices. Like you have you can imagine as a loaf of bread, you're actually splitting the file, right? You're splitting the loaf of bread into 4 parts. Okay? And the advantage that you get out of this is convenience. One is that you have lesser failure of less amount of failure for files, but at the same time you can actually parallelize your computation. Okay? For every single slice, you're going to you can process them independently of each other. So that's the biggest advantage that you get out of it. Okay, so so HDFS, when they say HDFS partitions, it actually literally almost means blocks. Okay, so 120 MB is a default partition. We'll look at various other times where partitions is used differently. We'll look at it tomorrow. But for all intents of storage, your 128 MB is your partition. Okay, and this will be used for as a computational unit. Okay, so in terms of Spark job, every single partition will be processed by one thread. Okay, and in terms of MapReduce in the old world, every single partition will be processed by one processor itself, one core. Okay, so that is the main reason we moved away from MapReduce to Spark. Okay, that's a different thing. So we have 10 cores and 50 GB. Okay, so resource manager is here, and then you wanted to you have several cores. You say, for example, this is 50 cores and 75 cores, and most often it's homogeneous, but sometimes it's different as well. So resource manager knows that, okay, this file that you're trying to process, say for example, say this file is about 256 MB. The file that you're going to process is actually could be split into two partitions. So the first partition you can process in this machine, which has have 10 cores. You're asked for 10 cores. So 5 cores and 25 GB, and somewhere here 5 cores and 25 GB. Okay, we allocate something like that. So the first partition gets processed here, and the second partition gets processed here. Okay, so you can process independently. That's the idea. The specifics are not important. What we need to know is that out of this context, what we need to know is that we need to remember that you are requesting certain amount of resources from Yarn, and it's up to Yarn to decide which machine it wants to run the computation first. And the second point is that your computational unit will always be the amount of the data that you're processing will always be done at the partition level, not at the whole file level. That is the most important thing you want to drive at. Okay. Anyone, any questions? Yeah.
So let's say we carry this forward to the fault tolerant concept, whereby sometimes same partition is distributed to several nodes,
Yes.
just in case one of it fails.
Yes.
Let's say one of it successfully run at a particular node. Does Yarn actually tell the rest to stop running, or does the other nodes also just run?
The other nodes will run, and Yarn will retry because one machine is down. Yarn will retry that amount of computation with another node where it has replica.
Yeah, let's say nothing is done. Let's say one of the nodes successfully run it first. Does the other standby partition or the same partition that has been successfully run will be cancelled? Or do we need to configure it to
I think I didn't get your question.
So let's say partition A distributed to node A, B, and C.
Okay.
And node A successfully run partition.
No, one partition will be processed by just one thread, right?
Yes.
So there is always just one node which is working on it. So in this case, this is partition A,
Yeah.
and this will be partition B.
Yeah.
Okay. And if this node while it's processing just fails, Yarn actually can have the your Spark has a capability to it will say to Yarn saying that okay, I think I lost my node. Can you give one more node? And then Yarn will give another node, and this partition can just go on compute, and then this will be processed by partition A. The second node will pick up the data.
So my question is actually like, what if it successfully run at partition A, then the rest of it will be cancelled?
No.
Use that one.
Per partition.
I'm sorry.
The code will only run on one partition.
Yes. The code will always run on only one partition. Yes, exactly. Only one partition. One thread per partition. And assume that this is a node which is running. If it fails, the rest of the partition can just still proceed. There won't be any cancellation. This partition alone will be retried in another node, and then that will finish the completion, so that the entire job gets finished to the completion.
Okay, thank you.
That's right.
One thing I don't understand is that the Yarn will send, let's say you ask for 10 core, right?
Mm-hmm.
Then you distribute it to a 5 core.
Yes.
The 5 core CPU power may not be matching up to the 10 cores CPU, right?
The 5 cores one?
No, you send to a particular node that has got 5 core processing power,
Uh-huh.
but you're actually asking for 10.
Yes.
But the performance of 10 might not be matching up.
Excellent point, excellent point. I actually bluffed. It's not 10 is not split into 5 and 5. You would specifically say that how many machines you want, and then in each machine how many cores you want. You'll be looking at it shortly when your Spark configuration. Yarn does not decide to split your 10 cores into 5 and 5. Okay? So when you're submitting a Spark job, you'll be looking at it maybe tomorrow. You will be specifying when you submit, you will say that I want 10 machines to run this job, and each of these machines should have 10 cores and this many GB of memory. You would be specifying that explicitly. And if you're saying that, now to your point, you said that 10 cores is not equal to 5 cores each. Yes, in which case if your program has a requirement of having 10 cores in a single machine, you would just say, I need one machine with 10 cores, and Yarn would be able to do it. Okay, that sounds very good. Cool. Anything else? Yeah. Ah, good point. We'll come to that right now. Okay. Oh, yeah, I'm really glad that you're asking the right questions. All right. So one other aspect of Hadoop is that when you look up the documentation and everything, people say that Hadoop brings computation to data. Right? I mean, that's a weird thing to say. Because what they mean is that because the data is huge and runs to petabytes and petabytes, you can't bring the data into the computation. So you can't say that I'm going to run my computation here, copy all the data to this machine in order to run. So you're bringing your computation to the data itself. So all these architecture which I was talking about. So we spoke about node manager, right? Sorry, we spoke about name node. Okay. Node is one thing, sorry. My artistic skills are not up to the mark. Alright, we have name node. Okay. Typically when you size your cluster, your name node and resource manager will be in two independent machines, because this name node has a huge memory requirement around it, right? Because it's going to store all the metadata into memory. So it needs a lot of memory. And then in your cluster, your resource manager sits here. This would be a completely different machine altogether. So this would be a physical box, physical 1, physical 2, and then you have your say name node. What is the slave for the name node? Anyone? Data node, excellent. Data node, okay, and then data node. Okay. All right, okay. So assume that you have two data nodes. So name node stores the data inside it, and then you're saying you're bringing the computation to the data, right? So resource manager has, and data node, if you carefully look at a data node, need not be a massive machine or anything like that. It's just single process which can accept data from the client and copy it to its own local machine, correct? So this is actually a simple process. This is just a process on a physical box. This is physical 3, physical 4. Okay? This is a single process on your data node. Resource manager, what's the slave for the resource manager? Node manager, okay. Node manager is also a daemon. What do you think node manager actually does? I mean, it just receives a request from the client, and then it creates a small little container for the process to run. That's pretty much it. So these are just Java daemons, which is running on this machine. And this one has your hard drive, hard drive, and this one has your CPU, I don't know what to do, CPU or memory or whatnot, okay? So that's all it does. So what you're actually doing is that you have data stored in the hard drive, and your CPU is here, right, somewhere here. So, and the resource manager manages this guy, and node manager, this guy as well, okay? So now, so when you say bringing computation to the data, right? So what happens is that when the client requests for, when the client submits a Spark job or an MapReduce job, so you say that which is the data that you're actually going to process. In your code, you specify what is the data set that you're going to process. And in this data set, you will see that shortly in the afternoon, you will imply which is because within the code you're saying that this is the data set that I wanted to work on. This is my input data source, right? So Yarn, you will request Yarn saying that, you know what, I mean, this is a HDFS file I'm going to work on. Can you please allocate the computation on those machines itself? Okay. So assume that in the first example we had this as data node 1 and data node 2, right? So you're giving your file, entire file, and now the next request is that you would ask Yarn saying that, you know what, my file is in data node 1 and 2. Can you please allocate the computation, the processing in one of these nodes so that my data is local? I don't need to copy data from other machines. And it's up to Yarn to decide whether at any point it has enough, it can honor your request. Okay? It's up to Yarn to decide. I mean, it may not. So because assume that there is a lot of computation happening in data node 1 and 2, there's no way it can do. So it will schedule to data node 3, in which case you need to copy the data from data node 1 into your local machine. Okay? So any questions?
So in that data node 1,
Yeah.
you don't have a space for the computation.
Yes.
So if you copy from data node 2, all the location there, they will find the memory location.
Yes, yes. It will copy the data. It will be a network call from one machine to this machine.
You can do internally.
You can do it internally. You don't need to worry about it. You can do it internally. So that is the abstraction that you get out of Yarn and Swift. Did that answer your question? No. Did. Resource manager will be a part of the cluster itself. So if you create 50 machines in your cluster for storing your data and computation, you will have a couple of machines which is a master of all these machines. This will be on the cluster itself. Right? So this will be. I can actually show. How can I show this? You know what? I mean, let me do that. I would strongly suggest not to take pictures of this one. So this is your cluster, right? I mean, I think you're using Cloudera, right? I mean, this one is Hortonworks. Hortonworks is another competitor for Cloudera. It is a Hadoop cluster. Okay. And then you have, you can see what are the machines here. Okay. So this actually cluster runs on, I don't know, 1, 2, 3, 4, 5, 6, 7, 8 machines. Okay. It has 8 machines in its cluster, and then there's a whole lot of services in your cluster. One is HDFS, we saw it just now. Another one is Yarn. We don't use MapReduce anymore, so that's an old one. But you also have some Spark components written here. And if you look at it, you will see that in this, where is it? Okay. Okay. So there are 3 data nodes here. Okay? This is a data node here, and you can see that there is a name node which is there in the cluster as part of the cluster itself. Okay? So there is a name node which runs on this machine, and then you can see that a name node is called HM0, which is head node, and then you can see that data nodes run on a different set of machine, which is WN034, which is worker node. It's their own terminology that they have. And if you look at Yarn, Yarn has this active resource manager. Everyone has a backup, and this is interestingly, the Yarn also runs on the same head node as the name node itself. Typically, you don't do that. This is just SIT environment, so we are free to do that. In production, you typically separate these two guys separately. Okay? This is a head node 0, wherein it runs your Yarn master, and then you have node managers, which is the slaves. There are worker node 3, 0, 3, and 4. You can see that there is an overlap between data nodes and the node manager itself. Okay? So there is this is how you typically do a cluster. I mean, this is a very simple cluster, but that's how it is. Okay? All right. Any questions? All right, cool. So this is the bottom line. So when people say that what do you mean by you take computational data? All it means is that it's a polite way, or it's a polite request that you're making to Yarn, asking, can you please put me in the same, run this computation on the same data node as it's where the data is stored. Okay? That's pretty much it. All right, now let's talk about what is the juice of the talk we are going to talk about is Spark. Okay? Why Spark? What is Spark? Spark is just the code, the same way you write R programs. You write a bunch of lines of code and then you submit that to Yarn, right, for running. That becomes, once you submit to Yarn, it becomes a job. Okay, so let's make one more thing concrete as well. Spark Summit. To answer your point wherein you mentioned that 10 cores and whatnot, and that comes here. Yes, a good example. Okay, that's Spark Summit, driver memory. And I just wanted an example. What the hell? Okay, so this is a good example if you look at it. So what you're saying is that I wanted to execute. I'm submitting a Spark job. You write some pieces of code. We'll look at this piece of the code for the rest of the day and tomorrow. Okay, how do you write this piece of code? So once you have a piece of code written. All right. So once you have this piece of code written. And then what you're going to say is that I'm submitting the Spark job and I wanted to run it on Yarn. Okay? And the reason why you're saying run it on Yarn is that actually you have the flexibility to run Spark job on your local machine, which you're already aware of because you're running from an IDE, correct? So which you can run it as a plain vanilla main program as such. So you're running it on, you can choose to run it on Yarn. Obviously you wanted to run it on Yarn because you wanted to scale to big data, right? And then after this, I will speak about what this is later. And then what you're saying is that each of these worker nodes, workers within Spark, which you call as executors, each of these workers should occupy 2 GB of memory. Okay? And then you're not specifying any cores, you can actually specify the number of cores that you wanted as well. And then you're saying that I wanted number of executors, number of workers to be 5. What it literally means is that I'm requesting for 5 machines. 5 machines, and each of this machine should have 2 GB. So your total of what you're asking is that you're asking for 10 GB of memory. Okay? And by default, the number of executor cores, the number of cores is just 1. So which means that you're literally asking for 5 cores and 10 GB. That's what this this particular command means. Okay? All right. All right. Okay. I think that's pretty much it. Any questions here? Can I safely understand you understood everything? Is it okay? All right, cool, excellent. At any point, I mean, if you lost midway, just pause and then we'll go through that, okay? Because it's just not about sharing your exams, okay? So we'll look at a bunch of stuff and let's forget about this, okay? Okay, so this is the most important thing which I want to talk about. Why Spark? Why did we move away from something called as a MapReduce in the past? Okay. So MapReduce is originated from a Google paper, I think it's 2004 or something like that. So Google had this problem to solve wherein they wanted to parallelize and run large-scale computation. Correct? So that is a whole ambition. Now what happens is that they can't. Because they can't run these computations on a single machine, they came up with something called as a MapReduce. The concept of MapReduce is very, very simple. Okay. So what they have is that we have assume that this is a loaf of bread which is like this. This is 1.txt for you. Okay, and then you know that there are 4 blocks, or once you say you call them blocks when they are stored. When you're running a computation, you call them partitions. Because you're literally partitioning them and then running. That's it. So this is called this is the first partition, second partition, third partition, fourth partition. So assume let's take a real world example. In this case, we are talking about this is a so 4 blocks. Assume so this file is a 512 MB file, right?